Okay, welcome everyone to the final talk in the series of final presentations for astronomical observations, techniques, and instrumentation. The last talk is being given by Sean Foster, who will be talking about bulge-to-disk flux ratios.
Thank you, Dr. Feiger. So as was introduced, the bulge-to-disk ratios of type SAB galaxies is what my project is about. This kind of comes from the importance of modeling, because I will be using GalFit to be able to get these bulge-to-disk flux ratios, which creates a model of the galaxy that I imaged. So the importance of modeling, I think, is quite explanatory. Galaxy mergers is a big thing. You figure out the rates of galaxy mergers, its outcomes, gas accretion, star formation. And then what I'm focusing on is more about the galaxy morphology, specifically type SAB. And then models can then go to spiral arms, rings, bars, and then the different types of bulges, spheroidal, dwarf galaxies, and all that sorts of stuff. So how does GalFit help in these modeling? So GalFit creates a 2D model of the fitted galaxy, and what's kind of cool about that is it creates, if you take the image and you minus the model from that image, you get a residual which kind of helps reveal hidden details in galaxies. If you see this GIF from the creator of GalFit, Dr. Peng, you can kind of see different layers of, I believe this is NGC 4111, which I think is pretty cool. Can also help give parameters for morphology types, which you can put those into simulations to get expected outcomes, and that helps with figuring out galaxy evolutions. So, as I said, my objective is to study bulge-to-disk flux ratios. And so I picked my targets from the RC3 catalog using Vizier, and had certain constraints to make sure I could see it from my observatory at home, and during times and that fit the parameters. So there came 12 galaxies, but as you can see, number 2 is missing, and that is the Andromeda galaxy. This is too big to throw into GalFit, so got rid of that, and so that leaves 11. This is the observatory in my backyard. It's a 0.6, which creates the telescope. I think we're all familiar with that. What's not shown here is the filter wheel, which of course would be right here. So the optical train, 4,723 millimeter focal length, fixed primary and movable secondary, and also have an S-Big camera. It's a 4K by 4K front illuminated, typical CCD camera. A whole bunch of information about quantum efficiency, and I'm focusing mostly in the luminance band, so that's, I think, about around 500. And then just to be able to make sure nothing goes wrong while I'm actually remote observing, so I will VPN to my observatory, say, okay, I want everything to run, and to be able to make sure weather or wind or whatever might happen doesn't destroy the telescope. There's a sky monitoring kind of little center there that makes sure that if there's any increased precipitation, clouds, it'll just close the dome up. So this means I can have it running all night without having to worry about it, and no one needs to be sitting in the observatory to make sure everything's running smoothly. Oh, and then I have an alert on my phone if anything goes bad. So on to the bulge-to-disk mathematics. What I'm doing is from my image, Galfit is creating a Circuit profile, and traditionally I believe it's Devakular, so n equals 4 for the bulge and n equals 1 for spirals. But as I later realized, this is incorrect, and keeping that fixed actually just creates problems. But using a bulge Devakular fit and then an exponential fit for the disk, you get this equation for the b to t, where this equation for the bulge to disk is b to t is bulge to total, by the way. And the bulge to disk, if you put in n equals 4, and the b parameter is also dependent on, and then it comes out to the b to t ratio. I think a lot of the constants and factors b and all this sort of stuff turn into 0.28 once you go from b to d to b to t. And if you look lower, b to t is just the inverse -1, so you think about it. The bulge to total plus the disk to total should equal 1. So that's an easy way to just kind of go between bulge to disk, bulge to total, or disk to total. So there were 11 targets. Forgot to change that on my slide. I used SkyEx to determine the RA index of my target and obtained a suitable guide star. There were 4 frames in the luminance, B, V, and R, and H alpha, all about 900 seconds, where the H alpha was longer. I didn't end up using the BR VNHA only because I had limited time. I was planning to do a little bit more with the information, find an easy thing to do with a lot of this, to find V minus V magnitudes for the classic galaxy that I was researching. I was thinking maybe I could do something with H alpha as well, so there's a whole bunch of different things I was trying to do with this. But in the end, only really used luminance frames to do find B to T, and didn't do anything else with it. So it's something I could definitely work on in the future. There are 10 biases nightly per bin. So for each bin, 10 biases. Darks, flats, using dome flats. And in total, took 14 nights and about 54 gigabytes of data. The only fraction of that was used. These are the targets, and this is 11 targets, this isn't 12. So the pipeline that I went through to get these models for my data were to first do the calibration where they're flat fielded, bias subtracted, darks. And then pinpoint, each time a picture's taken, I use pinpoint just to be able to make sure that it's looking in the right area. So that uses the UCAT4 database, which is from the United States Naval Observatory, I believe. I then create a master frame for each data point, and then use PixInsight to generate a point spread function for the image to be able to throw into XExtractor and Galfit. So on the XExtractor, first I use the first pass to get the XY coordinates, integrated magnitude, background values. Basically what you see here, but then what it gives me is the segmentation map. And the segmentation map is, if I have an image, it'll run through and say, okay, you have this many objects based on your parameters, and then sets all those objects to the value that it's given. So, sets its value to the object number that it's given. So if it runs through, you get 900 objects, you have 400. Your target is 400th object, then it'll change its value to 400. So it looks like this. If you kind of decrease the stretch, it just looks like everything's black, and then you have a whole bunch of white around. There's no subtlety, no gradients or anything like that. So this just, it's really easy for me to say, okay, I know that this is my target, this gives me the object number, and I can then, I'll go back to that, input that into GScripter, which then sends that to XGAL, and XGAL then just takes a little screenshot of my target. So that just creates a very small thumbnail, basically. Just an interesting anomaly from my calibration. I believe this is NGC 891, and while the, I don't know if you guys can see it here too well, here and there are artifacts of dust donuts moving as the filter wheel moved. And then at the same time, in the bottom right, you see this very bright spot and this line. That is C2013X1, which is a comet that just happened to pass by as I was taking this photo, which I thought was pretty cool.
So this image was taken by your...
Mm-hmm. And so yes, we get the thumbnail, and then I throw that back into S extractor again, and then this gives us the half-flex radius, ellipticity, elongation, position, angle, all that sort of good stuff that we need, and then input that information into Galfit, and that creates a fit and then a residual. And Gym2D I used. Gym2D has a package in IRAF, and that has some packages that includes GScripter, XGAL. So the second extractor run, this is just more information. This is to gain the information needed to put into Galfit, where the first extractor run was just get the thumbnail. I then put that information into Galfit the first time, and it gave me this. So I crashed. It turned out that the theta image needed to be 90 minus that, otherwise it crashes. So once that's done, I then get this. So this is NGC1. This is my first fit, and the error values just didn't make sense. So this is the sky values, this is magnitude, and this should be an EDU. So as you see, 41 EDU for the sky background with an error of 92,000. Didn't make sense. And the same thing with the, this is the R sub D, for the life of me, what words to that? It's this scale length, and then you have the R sub E, so that's the half-life radius. So as you see, the error for this is 10 times as much as what it was given for the radius. So that didn't make sense either. And then the residual had this weird artifact in the center. So nothing was making sense. Absolutely nothing was making sense. So I contacted Dr. Peng. He has a very nice Facebook page, and immediately answers your question at 1 a.m. and we'll stay up with you till 3 o'clock figuring out what's wrong. So figured out that my PSF was wrong, so I needed to generate a new PSF, because a whole bunch of the papers just said, yeah, just pick a point source in your image, you should be good. No, don't do that. So I had to generate a PSF. So I used PixInsight for this, actually, and I took 50 stars from an image that all had a MoFat distribution. So that's an unsaturated image where I think the Gaussian distribution would be more saturated. And then Gaussian distributions, you think about like a curve, it would be more wide at the tip, where this the MoFat would be sharp. So then generated the PSF. So you see that's the bottom right, it's the PSF. And so this is just comparing a good PSF for one of the images compared to the bad PSF, which is what I used before, which gave me that terrible fit. Once I changed that, I got an okay fit. It's better. You see the residual on the top right is the changed fit, where the bottom right is the old one. So it's a step in the right direction. And this gave me much better sky background values. The errors of radius didn't seem bad. So, and it made sense to me that the magnitude of the disk, or sorry, the magnitude in the bulge was lower than the magnitude in the disk, right? The bulge was brighter than the disk. So that made sense to me. But it didn't make sense when I started running through everything else. I got a whole bunch of weird values. No big errors. It seemed very certain in and of itself, but it was giving me things like the bulge radius would be, or the half-life radius would be like 300, where the disk scale length would be 10, and that didn't make sense. And I couldn't figure out how to change it. I ran it over, did multiple fits, tried to have upper limits in the disk scale length, and nothing helped. I was able to get 6 analyzed, 6 of the 11 galaxies analyzed, and so we have the bulge to total, the error, the bulge to disk, and the error. You can see the bulge to disk, which I was looking for. They're all over the place. Something's obviously wrong here. Going from 4 to 1 to, well, I mean, you guys can see it's a mess. So I still have a lot of work to do with this. In conclusion, just very inconclusive. Data needs more analysis. I need to understand GalFit better. There's a lot of subroutines that I can use to be able to create rings, arms, and upper bounds of the parameters to be able to kind of keep it in the area where it should be. And I'm not familiar enough with how that works. The CIRSIC profiles that were chosen, I think were wrong. When I made sure that those were not kept constant, I got CIRSIC profiles for the bulge of about 1 and the disk for about 0.5. And that seemed to give me a much better fit for a lot of them, but I needed to change a whole bunch of the values for the equation using getting the bulge to total and then bulge to disk. So all in all, there's a lot of work to be done in this project, and I feel like a lot of time can be spent trying to figure out how to be able to get a good fit and what actually makes a good fit. Because I mean, these errors are small, they seem good, but they don't make sense. There were a lot of references to be able to build my pipeline, figure out what I was doing. So. Okay, I think we have time for questions.
How much did that telescope in your backyard cost you?
I don't think he wants to think about it. Oh no.
It's my dad's baby. He retired early and decided he wanted to have some fun with him. We moved out to the country, so I'm in Northern Virginia, so about an hour outside of DC. So the seeing isn't too bad for that area, but I think it wouldn't have cost as much if my mom did not require it to be stone. If you actually go back to the so you actually see on the top left image. My mom wanted it to look good, so.
Well, at the very least, you need to be able to trick anyway.
Yeah. It's actually pretty cool because you have to. This has to be completely disconnected from the dome itself, so that if there's like an earthquake, it will be solid. But I don't know how much it costs. I'm guessing a lot.
Yeah, he doesn't want to talk about it either.
Okay.
So your original PSF, it kind of looked asymmetric a little bit. Do you have any guesses or reasons why that first try, went weird?
So this original PSF, it wasn't generated. It was just a lot of sources that I looked at to guide myself through this project just said initially just take a star from your image and throw that in as the PSF. And I think this is just an example of Poisson noise.
So just taking more of them, I guess, would make it more symmetric.
Mhm.
With all the statistics is done. And what program did you use to get the good one?
PixInsight.
PixInsight. Okay, thank you.
Oh, gee.
So, can you go back one slide, I think? Yeah, so those models, they looks like there's no disk add-on.
Right, so there's no spiral arms in this. That's what I was talking about at the end of the conclusion, is that there, after I started doing this, I realized that there's a lot more detail to the coding, and that I would need to put in a whole bunch more code to be able to say, make a disk, or not a disk, make spiral arms, this line, this
Yeah,
angle.
this one just is for elliptical kind of galaxy. That's why you
Yes.
are getting a very less amount of disk component because it's like big elliptic and small.
That's what I ended up realizing. By the time I was kind of like, this actually, I realized that whole other area, it
Also,
ability.
one thing I want to say is like in your image, you seem to have like really bright stars in the middle. Like this, if I understand the residual correctly, and it's for the first fit. So you may want to check to see if your objects are like in GN or something like normal.
I mentioned none of them were EGN or any sort of, I think it's just that was just a function of the bad PSF. And there are still some problems, especially in this one. The top right, you can see that there's a circle and a dot, and that's not supposed to be there. Other fits, the ones I did at 5 a.m. this morning were much better. And some not. So it was very random, and I think it had more to do with the parameters of the galaxy that I didn't have time to look up or change.
Does it also handle like inclinations?
Yeah.
Did you compare what the results of the ratios you got to like any published values, or
I couldn't find much actually, or at least for the galaxy type that
that you were looking at?
that I looked at. When I did actually find I won't call it a paper, someone's webpage had a graph of a whole bunch of different morphological types, and the bulge to disk, I don't remember if it was bulge to disk or bulge to total ratio, and they had a wide range. Now there was a steady curve upwards as it went to early type galaxies, or I guess not late type, the more elliptical type. But after I found that, I already had this sort of stuff, and then I realized, well, there's a wide range of values that you can have, although based on the morphological type, it will change. And that's why I was saying earlier that it would be better to compare this to other types of galaxies. If I got more data for each set and compared it with every single type of morphological class, then I would get a better idea of what it means.
I had a couple questions. Are your data saturated?
No, they're not.
Okay. The other question I had is, what happens when you run GalFit plus whatever other routines are in your pipeline on images of the same galaxies from other telescopes like Sloan or the digitized sky survey? Like for this galaxy, if you download a DSS image of this and you run your code, do you get the crazy?
I haven't tried it with other galaxies. I'd have to be careful. Or sorry,
Other data sets, yeah, same galaxy.
I would need to be careful though to be able to make sure that they had a similar. And you can't have a galaxy too large, right? So GalFit is pretty good at creating fits of really small galaxies. So let's say if you're using Hubble, you run really far. A galaxy with a high Z, right? You want it to be far away, and so I need to be careful if I got like a big telescope to make sure that it doesn't go over the image.
Yeah, well, I think in the DSS there's contiguous coverage, so you can cut out your own image area
Mm-hmm.
and just choose to have the area cover the whole galaxy. And
My computer died.
I presume Sloan would cover these. I don't know. But it's a good thing to do, right? Because
Yes.
you should do all these cross comparisons where you use other people's data and your code and, you know.
There's definitely a lot of work that needs to be done on this. And I think one of the biggest problems I had was actually just creating the pipeline itself. I had to go through so many different resources to be able to figure out what I was doing in the first place.
One tiny little question. What's luminance? Is that what you said? You use the luminance channel?
The luminance channel.
Yeah.
So that's it peaks in the green, very similar to V.
Okay, so did you say you had VVRI? Are those the filters you could use?
I actually do have data on BVR and
Right.
HF, but I don't have I.
Right, and you took those data using physical filters that
Yes.
get wheeled into your,
Yes.
in front of your CCD.
Mhm.
And to get the luminance image, do you get that without using a filter? You just
No.
have it wide open?
It is a filter, and I can't exactly remember exactly what the difference is. I think it's more for photometry. It peaks in the green, only a few nanometers away from the V band, and it's a little bit sharper.
But how do you define a physical filter, a piece of glass called a luminance filter?
Yeah. A Johnson Cousin filter that I had been using for photometry in the past.
Because I think that some CCDs that have filters integrated into the pixels, like a blue and a red and two greens, the Bayer type of arrangement, they can often create a luminance out of the greens because there are two green pixels, whereas there's only one blue and one red. And that makes it more sensitive if you only want monochromatic data. I don't know the answer, that's why I asked you, but
Okay, yeah,
it'd
I'm
be
not-
interesting to figure that out. Are there any other questions? Okay, let's then try it.